section 2.2, page 147. Polynomial functions of higher degree. Now, we mentioned this in section 2.1, but our textbook does not assume that we did the prerequisite chapter, so we're seeing a lot of review at the beginning of this chapter of things that we've already talked about because they were in that prerequisite chapter, but that's okay. It's a good opportunity for us to just go back through them again. So on page 147, they tell me that if you want to find the graph of a polynomial, yesterday we talked about what a polynomial is, and we looked at several different types of polynomials, but if you want to sketch the graph of a polynomial is going to be continuous. That means that you can draw it without having any holes or skips or jumps in it. You can draw it without picking up your pencil, basically, is a way to look at it. And they give you some examples here on page 147 of what polynomials would look like that are continuous, that don't have those holes and skips and jumps in them. Then over on page 148, they tell us that the polynomial functions that have the simplest graphs are monomials, mono meaning one, so basically it's a polynomial with just one term. They're monomials of the form f of x is equal to x to the n, where n is an integer greater than 0. So we're talking about like x to the second, x to the fourth, x to the 24th, x to the 104th, that type of thing. It's just that one term. In each of those cases, if I have x and I raise it to an exponent where that exponent is an even number, 2, 4, 24, 104, I'm going to get this same basic shape of my graph. Really, the only thing that changes is that it just starts getting a little broader down here at the bottom. So if you throw into your calculator y equals x squared and y equals x to the 100th, you'll see they have the same basic shape, but x to the 100th just has a little broader base down here. The same thing is true if you raise it to an odd exponent, like if you have x to the third or x to the 23rd or x to the 103rd. They're all going to have this same basic shape. The only thing that will happen is we typically call this a slide right in here, that we slide through instead of going straight through. But typically that will be the place where this gets a little broader. So it'll be a little flatter right in here. So again, you could throw into your graphing calculator y to the third and y to the 103rd and see they have that same basic shape. So for example number 1, they asked me to just sketch the graph of a couple of polynomial functions. And so for the first one, they give me f of x is equal to negative x to the 5th. So the first thing I have to figure out is which one of these two scenarios we were just discussing is that function going to follow. Is it going to look like the first one, or is it going to look like the second one? The second one, right, because it's x to the 5th. It's an odd exponent. And then what does a negative out in front of the function cause? A reflection, right. Reflection in what? The x-axis, right. If this were inside parentheses where that whole negative x was being raised to the 5th, where we'd put a negative just in front of x and raise that to the 5th power, that's like putting a negative into the function, negative x in the place of x, then that's reflection in y. So this one is reflection in x, so I could come up and say, okay, let's draw this exact same curve reflected in the x-axis. So if I did that, this piece would reflect down here, and this piece would reflect up here. So that would give us negative x to the 5th. There are some functions that are symmetric both about the x-axis and the y-axis. This is one of those. If I had taken negative x and put it in the place of x and raised it to the 5th power, I would have gotten negative x to the 5th. So you can also see, just for fun on this one, that if you reflected this in the y-axis, you would have gotten that same thing as well. All right, look at the next one. The next one, we've got g of x is equal to x to the 4th plus 1. So let's start with just the base function, just the monomial. G of x is equal to x to the 4th. Is that going to look like the first one or the second one? The first one, right. So it's going to look like this. And then what does that plus 1 right there cause? Vertical shift, good. So yes, a vertical shift of a positive 1 or a vertical shift up 1, exactly. All right, look at the next one. For the next one, again, our base function is x to the 4th, so that's that same one that we were just working over here a second ago, but this time what does that plus 1 cause? A horizontal shift, right? Horizontal shift of what? Negative 1, right. So I could draw that exact same function with a horizontal shift of a negative 1. So come over to negative 1 and then draw the same thing. So going back to what we had learned on page 100, if we memorize those 6 graphs, then we could shift them and reflect them. Basically, they've just given me 2 more forms here that I could add to that. And this is going to work anytime I have a monomial raised to where I've got like x raised to a power, whether it's even or odd, I'll know what that's going to look like. All right, back in section P4, I had given you this chart. So literally I just lifted it out of our notes from there. But in P4, we had talked about the different ways to classify our polynomials. And so they go back through and give us a little bit of that here in this section as well. But basically, if you have a degree of 1, you have a linear equation. Degree of 2, quadratic. Degree of 3, cubic. Degree of 4, quartic. And we had kept on going. Degree of 5, quintic, and so on. We also had noticed at that point that whatever the degree is, it's going to have 1 less turn. So if it has a degree of 3, it's going to turn 2 times. And sure enough, when we graph a cubic, yeah, there's 1 turn and there's a second turn. The other thing that we had seen was that the leading coefficient tells me which way my graph is going to end. When my leading coefficient was positive, my graph ended up, and when my leading coefficient was negative, my graph ended down. So we observed that back in section P4, but they actually teach us that on page 149 in the leading coefficient test. So on 149, they tell me that your leading coefficient will tell you how your graph is going to end. Now, when we looked at how the graph would end, we could get a good idea of how it was going to begin as well. Because if you'll notice, everything that had an odd degree, 1, 3, 5, 7, 9, anything that had an odd degree started and stopped in opposite directions. So if it ended going up, then it started going down. Or if it ended going down, then it started going up. Whereas things that had an even degree, like 2 or 4, if they started up, they also ended up. If they ended up, they also started up. Okay? If they ended down, they also started down. So we can put those 2 ideas together. The leading coefficient tells me how it's going to end. If it's an odd degree polynomial, it's going to start and stop in opposite directions. If it's an even degree polynomial, it's going to start and stop in the same direction. Let's put those 2 ideas together, and then we have a really good idea of what our graph is going to look like before we even begin. So example number 2, they tell me we've got f of x is equal to negative x to the 3rd plus 4x. If this was just negative x to the 3rd, I could do what we were doing at the very beginning of this lesson, okay? Is it match pattern 1 or pattern 2, and did I reflect it or shift it or whatever? But because it's not just a monomial, it's a binomial, I have another term on here, then that doesn't work. I need to then think of it in terms of what we were talking about up here. So I can look at this and I can say, okay, my leading coefficient is negative. If my leading coefficient is negative, which way is this going to end? Going down, right. Then I can look at it and say my degree is 3. So since that's an odd degree, it's going to start and stop in opposite directions. So if it stopped down, it's going to start up. And I'll also know that because it's a degree of 3, it's going to have 2 turns. So I can say, okay, I want to start up, I want to turn twice, and end going down. And that will be the basic shape of that graph. That may not be where it is on the Cartesian plane. It may actually be drawn up here somewhere or down here somewhere, but that will be the basic shape of that graph. All right, look at the next one. For the next one, we have f of x is equal to x to the 4th minus 5x squared plus 4. And I've just kind of lightly crossed out the minus 5x squared plus 4 because in order to determine what this graph is going to look like, I need the leading coefficient and the degree, right? What comes after that is pretty much irrelevant for what we're looking at right here. So if I look at x to the 4th, using my leading coefficient test, what's your leading coefficient?
1.
Positive 1, right. So how is this going to end? It's going to stop or end going up, right. And since its degree is 4, is it going to start and stop in the same direction or opposite directions? The same, because it's even, right. So when it has an even degree, it starts and stops in the same direction. So this is going to start up, right. And since it's a degree of 4, how many turns is it going to make? 3. So I can say, okay, I'm going to start up. I'm going to turn 1, 2, 3 times, and I'm going to stop going up. And again, it may not look exactly like that. This one may go way down here, and this one may just go down here just a tiny bit. That whole graph may be up here somewhere instead of down here, but at least I have the basic shape. So if I'm trying to make an XY chart or something, I've got a huge head start. All right, look at the next one. For the next one, we've got x to the 5th minus x. So what's my leading coefficient?
1.
Positive 1. So how's this going to stop? Up. What's its degree? So how's it going to start? Down, right. It was odd, so it's going to start and stop in different directions. And how many turns is it going to make? 4. So I could go through and I could say, okay, it's going to start down. I'm going to turn 1, 2, 3, 4 times, and I'm going to stop up. So I think that's what that looks like. And I happen to look at that example in the textbook, or I happen to throw that in my calculator just to check it, and that is not what that graph looks like. That graph looks like that. And you're like, well, hang on. Okay, it is starting down and stopping up, but it's supposed to have 4 turns, and it only has like 2 turns. That's supposed to be like the graph of a cubic. That's not supposed to be the graph of a quintic. Why does it look like that? Well, when we talk about these rules, about the number of turns that it's going to make and that type of thing, that is a general rule, but there are going to be exceptions to that rule. And some of the exceptions to that rule come from, like, think about what we talked about at the very beginning of this lesson. Like when you had x to the 4th. That didn't have 3 turns in it, right? The reason for that is because you are getting all 4 of your solutions at the same spot. The reason that my graph has to turn, back here, I have 1, 2, 3, 4 x-intercepts, right? The fundamental theorem of algebra says whatever the degree of your polynomial is, you're going to have that many solutions. So if I have a degree of 4, it has to have 4 solutions. It has to have 4 x-intercepts. So I can go through and say, okay, I've got 1, 2, 3, 4 x-intercepts. In order to cross my graph, my x-axis 4 times, it would have to turn 3 times. That's the general rule. But what are some of the exceptions to that rule? Well, what if I have a double root? What if I have 2 solutions at the same spot? Then my graph is going to behave differently. What if I have a triple root? What if I have 3 solutions at the same spot or 4 solutions at the same spot? I'm not going to have 4 different x-intercepts at 4 different places on the graph that I'm trying to get to that I have to keep doing all these crazy turns to get to. What if I have imaginary solutions? I mean, I can have solutions that aren't real, right? And you can't graph imaginary solutions in the Cartesian plane. I'm not going to have x-intercepts for those. So if I have 4 solutions and 2 of them are real and 2 of them are imaginary, that would be all 4 of my solutions, but there aren't going to be 4 x-intercepts. And my graph isn't going to have to turn all those different times to get to those x-intercepts. So that's why this is a general rule, but that's why there are exceptions to that rule. So for instance, let's say that we go back to the pattern that we had at the very beginning of the period, x minus 2 to the 4th, all right? If we look at the base graph, x to the 4th, we said that that would follow pattern number 1, and that 2 is going to cause a horizontal shift of a positive 2. So I know what that graph would look like, but that doesn't look like what we talked about up here, right? The reason for that is if I were to actually solve x minus 2 to the 4th, I would get x equals 2, x equals 2, x equals 2, x equals 2. It does have 4 solutions. It is following the fundamental rule of algebra. It does have 4 solutions, but they're all 4 at the same spot. So that's why it's not making all of those crazy turns to get to all the different places. Okay? So we'll be looking more at that tomorrow about how to graph a single root and a double root and a triple root and that type of thing. But that's why sometimes these aren't going to go according to plan. All right? So once I know the basic shape of my graph, how do I know where to draw it? You know, we talked about this might be the basic shape of this graph, but it might actually be up here somewhere. Or this may be coming way down and this be just shallow right here. So once I get the basic idea of what it's going to look like, how do I know where to draw it? Well, I can use my x-intercepts for that, right? X-intercepts, solutions, roots, zeros, all synonymous terms. So for example number 3, they give me f of x is equal to x to the third minus x squared minus 2x, and they ask me find all the real zeros. Okay? The zeros are just where the function is equal to 0, the solutions, the roots, the x-intercepts. So we just want to solve this thing, right? So what's the first thing that we're going to do? Yeah, let's start with thinking about its basic shape, and then absolutely, if we want to solve it, then we will go through and factor out an x. So let's think about its basic shape. Because the leading coefficient is positive, which way is it going to end? Up. And because it's odd, which way is it going to start? Opposite, right? So down. So I know its basic shape, and it should have, if it follows the rules anyway, it should have how many turns? 2. So this would be its basic shape. I don't know exactly where that thing goes on the graph, but that's what it's probably going to look like. So I'm going to come back over here and I'm going to solve that equation because those solutions will be my x-intercepts. So as you said, to solve that, the first thing we would do is take out our greatest common factor. So we have a common factor of x. And then we could solve our quadratic. If it'll factor, fine. If not, then I'll use quadratic formula. So will this one factor? All right, what's it factor to? X minus 2x plus 1. And then we'll set each of those factors equal to 0. And we'll get 0, 2, and negative 1. Those are our zeros, our solutions. And what do those look like on the graph? X-intercepts, yes. So we can come over and we can say, okay, I had a solution at negative 1, I had a solution at 0, and I had a solution at 2. So I know those are going to be my x-intercepts. I also know that my graph is going to start down. It's got to come up through that x-intercept. It's going to turn twice, so there's one turn to come back down through that next one. And there's the second turn to come back up through that last one and then going up. So that'll give me an idea of where to draw my graph. There are times, however, that genuinely the best way to do this is just to use our graphing calculator, and they'll tell us that. So like in example number 5, it says use a graphing utility to find all the real zeros of x to the 5th minus 3x to the 3rd minus x squared minus 4x minus 1, and to obtain the graph. Okay? So just a reminder of how we would put that in our calculator. We could go to y equals, so grab your graphing calculator if you would. And we'll put in that equation. So we had x to the 5th minus 3x to the third minus x squared minus 4x minus 1. And I'm going to start with a zoom 6. And so there's what our graph looks like. I can't see the itty bitty bottom of that one curve, and I have excess on the sides that I don't really need. So if I wanted to, I could go back and manually set my window and shave off a few of my x's. So like for my x's, maybe I just want to go from -6 to +6, counting by ones. And for my y's, remember I just needed to go a little lower. So maybe I want to go to -15 and see if that will give me my whole graph. It's just a little bit of trial and error. So then I get a little better picture of my graph. I can see everything that's going on there. All right. And remember the way that we can use our calculator to find those x-intercepts. We'll find this first one over here that's kind of by -2. The way that we do that is we do second trace, and we go to 0. And it's going to ask me for a left boundary and a right boundary. Because there are several x-intercepts here, it needs to know which one I want it to find. So since I'm looking for this guy right here, that's about as close to it as I can get. So I'll go a little bit to the left and hit enter, go a little bit to the right and hit enter, and then guess, and it will tell me that precise x-intercept. And then of course we could repeat that process for as many of them as we need to. So again, what we did there was we put the equation into y equals and graphed it. If you want to recenter your window, you can. And then we went to second trace, which was the calculate menu, chose option number 2, 0, gave it a left boundary, a right boundary, and a guess, and it told us that x-intercept. And then of course we could repeat that process for as many x-intercepts as we had. Okay, so I know we've done that repeatedly this year, but just good review for us. All right, so here is our homework for tonight on pages 156 and 157.